Welcome. This is a session on ESE steady state analysis of network theory, and we are dealing in this series the question number 11 as shown here. Previously, we have seen the complex power, the real power, the reactive power, everything. Now, here there is the next question in this series. So, let us see the question. Find the reading of the ideal voltmeter in a given circuit. So here the circuit is given. So first of all, what is an ideal voltmeter? The ideal voltmeter is the voltmeter. Voltmeter actually means it measures the voltage between 2 points. So ideal voltmeter is the voltmeter in which the internal impedance is equal to infinite ohms. That is, in infinite ohms means the resistance is very huge, no current will flow through it. So the current flowing through it is 0, 0 amperes. Now, if you observe closely this circuit, it appears in the form of a bridge. Is it as a balanced bridge? Let us check. The opposite resistances we multiply. Okay, here the opposite resistances are J1 into J1 is equal to minus J1 into minus J1. Okay, that means minus 1 is equal to minus 1. So the bridge is balanced. The bridge is balanced. If the bridge is balanced, normally in the Wheatstone bridge, these 2 points, through these 2 points, there must be zero current. Is it true? Yes, there must be zero current flowing through this. That means the point A and point B must have the same resistance, and the voltmeter must measure the reading of voltmeter should be 0 volts. But that is not true here. Okay, I will explain the reason. Take an example like this. Point 0.5, same circuit with different values I will take like this. So this is J3 ohms, this minus J4 ohms, this is minus J6 ohms, and here is J8 ohms. And let us take a voltmeter here. Okay, here if you observe, let us apply the same Wheatstone bridge concept. So J3 into J8, J3 into J8 is equal to minus J6 into minus J4. That is 24 is equal to 24. Here in this case, the voltmeter, the points A and B again here, the voltage across these points is 0, and hence the voltmeter reading must be 0 volts. This is correct, but this is not correct. The reason is, if you observe the branch voltage here, okay, so J1 and minus J1 adds to 0, and here minus J1 and J1, it also adds to 0. So that means effectively the resistance here, our impedance here is 0, and in this branch also the impedance 0. So in the above case, the branch is physically short circuit, we should not apply the bridge balance formula. Okay, Wheatstone bridge formula is not applied here. Here in the below case, the resultant impedance is different. It's a non-zero value, and this is also non-zero value. So if non-zero value exists, that is you can apply the Wheatstone bridge balance formula. Okay, I hope you got it. So let me remove this. Okay. So if this effective circuit is drawn, that means the branch here has zero impedance and here also has zero impedance. So the circuit looks like this. This is 100 sine omega t. This is zero impedance and this zero impedance. And effectively it's a short circuit. Okay. So this is what 0.5 ohms. 0.5 ohms. So the current here is, let us take I. If I take this as reference voltage 0 volts, as this is short circuit, here also it is 0 volts. Okay, so the maximum current, why maximum current? Because the maximum value of voltage is will be 100, as the sine curve, sine into 100 is the maximum value will be 100. So the maximum current is like this. It is this voltage minus this voltage divided by 0.5. Okay, so that will be this voltage. I can take it as 100 angle 0, right? So 100 minus 0, this is 0 is here, 0 divided by 0.5. This effectively comes to 200 amperes. Okay, now the voltage here, the V, the voltage here, let us take this as voltage across minus J1. So this point as voltage across J1, voltage across minus J1, and this voltage is J1. So the voltage here will be voltage across minus J1 minus voltage across J1. Why I am doing that? Because this voltage is 0 and this is also a reference. Both are same. So my V minus J1 minus VJ1 is the voltmeter reading. So sorry. So V minus J1 is what? The voltage across this particular element. So if 200 amperes is flowing through this, according to the current division rule, here it should be 100 amperes and here it should be 100 amperes. So it should distribute evenly, equally, or about the two branches. So 100 amperes will flow through here and 100 amperes will flow through here, and the same 100 amperes will flow through this impedance also. So V is equal to I into Z, so the formula will be 100 into minus J1. So this will be minus J100 volts. The voltage across J1 will be, that means this particular impedance. Same 100 into J1. That means J into 100 volts. So what is the value of voltmeter? So V is equal to this value minus this value. That is minus J100 minus of J into 100. That is minus J200 volts. So this is what maximum value of V. Why we started with the maximum value of current and we got a voltage which should be the maximum value of V. And one more point to note here is the voltmeter only reads RMS value. Voltmeter only reads the RMS value. So VRMS asked in the question. So reading of the ideal voltmeter, VRMS is peak value divided by root 2. So 200 by root 2. So peak value is magnitude of this, that is 200. So 200 by root 2 it will come as 141.42 volts. Okay, so the reading of the ideal voltmeter is 141.42 volts. Okay, let us go forward. So in this chapter we learned many things, and now I will summarize all the concepts that we have learned. Okay. So summary of what you have learned till now. First one, the resistance element R. So impedance here is the same R ohms. Here the voltage and current are in phase. And the power is equal to I RMS square into R, or V RMS square by R watts. Okay. Second one. Next, inductor. If you take the inductor, the impedance across the inductor is J into XL, where XL is given as omega into L. In an inductor, the voltage leads current by 90 degrees. Here XL is known as what? Inductive reactance. Inductive reactance. So through an inductor, the real power is always zero, and the imaginary power, reactive power, is Q is given as I RMS square into XL. So or V RMS square by XL. The units of reactive power or Q is volt ampere reactive. Okay, VAR. Next element is capacitor. So impedance across capacitor is minus J into XC, where XC is 1 by omega C. Here current leads the voltage by 90 degrees. Current leads the voltage by 90 degrees. Here XC is known as capacitive impedance. The real power to the capacitor is 0, and the reactive power is I RMS square into XC, or V RMS square by XC. Same. So if you consider the above inductor case and the capacitor case, the formula remains almost same. Okay, let us move forward. Next, let us see about the series RL circuit. Series RL circuit is represented like this. This R and this is L. Here the impedance is mod Z followed by the angle pi, where mod Z is root of R square plus XL square, and pi is tan inverse XL by R. Or if you multiply by I on both on numerator and denominator, it becomes tan inverse VL by VR. Here the current is V by Z angle pi. That means it becomes V by Z angle minus pi. That is I lags voltage by pi degrees. The I lags voltage by pi degrees. So what is the leading here? In the RL circuit, in it as inductor is present, the voltage will be leading and current will be lagging. Here the real power is I RMS square into R, or V RMS I RMS into cos pi, and Q will be I RMS square into XL, or that is Q is reactive power. So VRMS into IRMS into sin pi. Here VRMS is the current flowing through inductor, IRMS is the, sorry, VRMS is the voltage across the inductor, and IRMS is the current flowing through the inductor. Okay, next. So we have seen about P and Q. P is the real power and Q is the reactive power. So one more term is there, yes. S is known as complex power. Complex power is P plus or minus JQ. So if or P plus JQ, if you take, Q is positive for inductor and Q is negative for the capacitor. And apparent power is denoted by mod S. It is given as root of P square plus Q square. Okay. Now, supply voltage. Voltage. Supply voltage mod V. So for this, for the same RL circuit, so suppose R is like this, L is like this, and it is connected to a supply voltage V. So this is R and this is L. Okay. Here, same current is flowing through both the elements. So I take the I directionals like this, and VR will be in phase with I, and VL will be at right angle. Why? The VL leads the current by 90 degrees. So the effective voltage will be the sum of VR and VL. So it will be like this. That is the supply voltage V. Okay, this VR and VL, the vector sum of both of these gives the supply voltage V. So the mod of the supply voltage is nothing but root of VR square plus VL square. Here VR is V cos pi and VL is V sin pi. So that we get from vector where V makes an angle pi with a VR. So VR is V cos pi, resolution of vectors, and VL is V sin pi. Okay. Next, we are going to look at series RC circuit. Next one is series RC circuit. So first one is series RL circuit. Now it is series RC circuit. So series R and C. Okay. Here the impedance is mod Z angle minus pi, and mod Z is root of R square plus XC square. The pi is tan inverse minus XC by R. Or you can write minus pi is equal to tan inverse XC by R. Both are same. So tan inverse of, we multiply with I on both sides because same current will flow through them as they are connected in series. So it will be VC by VR. So the current I is given as V by Z. That is V by Z mod Z into minus pi. It is V by mod Z into pi. So as the angle is positive here, that means what is leading? The current leads the voltage by pi degrees. Okay. Current leads voltage by pi degrees. Now coming to the reactive power. The reactive power here will be I RMS square into XC, or VC RMS into IC RMS into sin pi. The apparent power here is root of P square plus Q square. Where P is the real power, that is power absorbed by the resistor, which is I RMS square into R. Okay. So the apparent power is like this. And if you draw the phasor diagram for this circuit, what it will look like? So the VR will be along the positive horizontal direction, and VC is below VR, because here the current will be in this direction, and the voltage across capacitor lags the current by 90 degrees. So the resultant voltage will be like this. Okay. If you want, that resultant voltage is nothing but source voltage. So the source voltage, modulus of that source voltage is what? Root of VR square plus VC square. Here VR is, so this angle is pi. VR is what? V cos pi. And VC is V sin pi. Okay. Is there any doubts in this? I hope it is clear. Next circuit is, so the next circuit is series LC circuit. Next circuit is series LC circuit. The series is like this. It is combination of L and C. L is here and C is here. Okay. The impedance here is given as mod Z into pi, or the Z is mod Z into minus pi. Why? There are two cases. The resultant impedance is the combination of J into XL minus J into XC. That is J into XL minus XC. If XL is greater than XC, that means it's an inductive circuit and pi will be positive. If XL is less than XC, then it is a capacitive circuit. In that case, the pi will be negative. So first case is if XL is greater than XC, then it will be an inductive circuit. In inductive circuit, what happens? The pi is positive, and also the I lags V by 90. I lags V by 90. Here, if you draw the phasor diagram, the current through both the elements is same. So I draw I in the horizontal direction like this. I is horizontal, and VL is always above I. That is, VL is 90 degrees ahead of I, and VC will be downwards. That is, voltage in a capacitor lags the current by 90 degrees. As I am saying that it is an inductive circuit, VL is given a higher value. That's why it has a longer arrow than the VC. Now the power here, that is the real power, is 0. The reactive power is IRMS square into XL minus IRMS into square into XC. That is IRMS square into XL minus XC. Okay. Above case is when XL is greater than XC. If XL is less than XC, then what happens? It will be a capacitive circuit. In capacitive circuit, the pi is negative. Okay, so taking the same circuit here, what will be here? In this circuit, VC will be a longer line than VL. So VL will be a shorter line and VC will be a longer line. And the effective circuit becomes here, pi is like this, it becomes VC minus VL. VC minus VL. And the impedance here is mod Z angle minus pi. That is, I leads voltage by 90 degrees. So the resultant voltage is downwards. The current is in the horizontal direction. That means what? I leads the voltage by 90 degrees. Here, the reactive power is given as I RMS square into XC minus XL. I RMS square into XC minus XL. Now, so we have completed series RL circuit, series RC circuit, and series LC circuit. Now we are going to look at series RLC circuit. So series RLC circuit looks like this. This is R, this is L, and this is C. RLC circuit. So it may be connected to a source voltage V. The resultant impedance here is R plus J into XL minus XC. Let us take case 1. If XL is greater than XC, I lags V by pi degrees, where pi is the angle between the source voltage and the current, I total current flowing through the three elements. So here the pi is tan inverse XL minus XC by R. Okay, XL minus XC by R. In case 2, if XL is less than XC, then I leads voltage by pi degrees. Here the real power is VRMS into IRMS into cos pi. The reactive power is VRMS into IRMS into sin pi. And the case 3 occurs when XL is equal to XC. If you go above, how the circuit looks? It looks like this. So XL is equal to XC. That means reactance of inductor is equal to reactance of capacitor. So in that case, J into XL will be the impedance across the inductor, and the impedance across the capacitor will be minus J into XC. Okay. If both adds, what it will become? J into XL minus XC. If XL and XC are equal, this adds to 0. Okay, adds to 0. Adds to 0. If Z is, then Z, the effective impedance will be what? Only the resistance, that is R. That is, the circuit will be resistive in nature. And this is the condition for impedance. Sorry, condition for resonance. Resonance is a part of the series RLC circuit. We'll elaborately discuss about it in the next session. This is the condition for resonance. In this case, the V and I are in phase. Why? Because the effective impedance is only due to the resistance. In resistance, the voltage and current will always be in phase. Only power, real power exists here, and the reactive power will always be 0. Why? Because the reactive power is I RMS square into XL minus I RMS square into XC, which adds to 0. Okay, next. Next, we move on to the parallel circuits. So we have covered the four kinds of series circuits: RC, RL, LC, and RLC. Now we move on to parallel RL circuit. So parallel circuit means there is the resistance R, and this is the impedance of the inductor, that is J into XL ohms. So let us take a source current here. Okay, a source current is supplying current to both of these, which will be divided among these two impedances, and the voltage across both the elements will be same. Okay, here the effective impedance, instead of impedance like in the previous examples, we take here admittance. Why? Because in a parallel circuit we can add two admittances. Suppose the admittance across this branch is y1 and admittance across this branch is y2. So we can add the admittances in parallel, y1 plus y2. So admittance across this particular branch is G, and admittance across here is, admittance is nothing but inverse of reactance, or sorry, invert of impedance. 1 by R, 1 by JXL is also written as minus J into BL. So BL is 1 by XL. Okay. So here the effective admittance Y is Y1. Y1 is what? G. And Y2 is minus J into BL. So we can write it as minus J into BL. So BL is 1 by XL more, or sinus. Here the effective admittance is mod Y into angle minus phi. Okay. So because for inductor the impedance will come as positive angle and admittance comes as a negative angle. Okay. So here mod Y is nothing but root of G square plus BL square, and pi is tan inverse of BL by G. BL by G. That is tan inverse of IL by IR. How it becomes? If you multiply, or if you, so V is equal to I into Z, right? I into Z means I by B. That means susceptance. So if you multiply V and B, I will get I. So if you multiply both sides by voltage across both the elements, which is same, so you'll get IL by IR here. So pi is also tan inverse IL by IR. So in this case, as it's an inductive circuit, what happens in an inductive circuit? In an inductive circuit, which one leads? Voltage or current? Obviously, voltage leads in the inductive circuit. That means the current lags voltage by pi degrees. Here the real power V is equal to V RMS I RMS into cos pi, or in another form we can write P is equal to IR RMS square into R. The reactive power is given by V RMS I RMS into sin pi, or the same reactive power is given as I RMS square into XL. So this is the reactive power which is observed only in the inductor. So what is IRMS here? It's the RMS value of current flowing through the inductor. Yes, it is current through the inductor. If you go further in this circuit, if you draw the phasor diagram, You draw the phasor diagram. In the phasor diagram, the always in a resistance, the current through the resistance will be phase with the voltage across the resistance, which is VR. In this case, VR and VL are same. Let me take it as V. And the current through the inductor lags the voltage by pi degrees. The current through the inductor lags voltage by pi degrees. So IL is below V. So the current resultant current will make an angle pi with the horizontal. That resultant current, magnitude of that resultant current is root of IR square plus IL square. Okay. Now, if I see the power factor in a parallel RLC circuit, let me minimize this. Okay. If I take the power factor here the power factor is so, yeah, this here the power factor where we are. So we are at the power factor always will be cos pi. So the cos pi here is this is a parallel circuit. It is given as G by Y, where G is the conductance and Y is the admittance. It's also given as IR by, that is current through the resistance divided by the total current. Here, as the current lags, the power factor also lag. So here the apparent power is given by root of P square plus Q square. We have already seen what is P and what is Q. Okay, clear? Okay, we shall move on to the next circuit in the parallel series. So parallel RL is over, and next we will deal with parallel RC circuit. Next one is parallel RC circuit. In the parallel RC circuit, how can we draw this? There is a parallel element R which is in parallel with the capacitor C. And let us take the source current as I. Here the admittance is what? Again Y1 plus Y2. Y1 here is, as there is the resistance, Y1 here is G, and here the impedance is minus J into XC. And obviously the Y2 will be what? 1 by minus J into XC, that is J into BC. So here Y2 will be plus J into BC. So BC is 1 by XC more. So this Y, when written in a phasor form, we can write it as magnitude of Y angle pi. This pi is here plus pi. And observe that in the parallel conductive circuit, the angle is plus pi. Whereas in series RC circuit, the angle will be minus pi. So the magnitude of admittance is root of G square plus BC square, and pi will be tan inverse of BC by G. Here the current leads the voltage by pi degrees. So why the current leads? Because it's a capacitive circuit, either in series or parallel. If it is a capacitive circuit, always the current leads. The voltage lags. Here, the P and Q, the real power and capacitive reactive power are same as in the previous formula. The power factor is also same, which is cos pi, that is equal to G by Y. But here, the power factor leads. Power factor leads. That is what? Current leads voltage. Power factor always implies current, which leads the voltage by pi degrees. So if I want to draw a phasor diagram, looks like this. So in this circuit, the let current IR flows through the resistance R and IC flows through the capacitance C. So IR will be in the horizontal direction and V is the voltage across the resistor, and IC will be 90 degrees to the voltage. Why? The current in a capacitor leads the voltage by 90 degrees. So the resultant current will be this, which makes an angle pi. Here mod I is nothing but root of IR square plus IC square. So the IR here will be I cos pi, IC here will be I sin pi. Okay. So this is about parallel RC circuit. Now let us move on to the parallel LC circuit. So next one is parallel LC circuit. So in a parallel LC circuit, the L will be in parallel with C. This is L and that is C. Here the admittance is J into, obviously Y1 here is J into XL, so minus J into BL. Here the admittance Y2 will be J into BC. So the resultant admittance will be what? J into BC minus BL. It is susceptance in a capacitor minus inductive susceptance. So let us take the case 1. Case 1 is if BC is greater than BL. If BC is greater than BL, the circuit is capacitive in nature. Okay, that means the current leads the voltage by 90 degrees. Current leads the voltage by 90 degrees. So if you draw a phasor diagram, the I will be like this. I is the current, net current. Okay, and current flowing through inductor is IL. Current flowing through capacitor is IC. And the voltage across both the elements are same. Let us consider it as V. Okay, V. Now the current is in the forward direction, okay, horizontal direction, which is in same phase with the source voltage V. And first element is inductor. In an inductor, the voltage leads, that is the current lags. If the current is lags, we will draw the IL downwards. Okay, and in capacitor, the current leads. That means you draw IC in the above direction. The current leads. And the net value will be what? And the net value will be above. Okay. Net value will be, suppose BC is greater than BL. That means IC is greater than IL. Why? Because uh, if you multiply both sides by V into BC is greater than V into BL. V into BC is nothing but IC. And V into BL is nothing but IL. So IC is greater than IL. As IC is greater than IL, IC will lead. IC minus IL is the net phasor which will be in the upward direction. Am I not true? Yes. It is in the upward direction. That is the mod of so that is the mod of net current will be IC minus IL, which will be in the above direction, and will be like this. So coming to the case 2. In case 2, if BL is greater than BC, BL is greater than BC, the same occurs here, whereas the change is as BL is greater than BC, IL will be greater than IC, the downward value will be more, and the resultant current becomes what? IL minus IC here. IL minus IC. That is here, the current lags the voltage by 90 degrees. See, the resultant current is in the downward direction. Okay, the resultant current will be like this, which makes an angle. Sorry, the current VIL minus IC lags the voltage by 90 degrees. Okay, this is about the parallel LC circuit. Let us move ahead. Next one is parallel RLC circuit. Parallel RLC circuit. So here R is here, L is here, and C is here, and all the three are in parallel. And the resultant admittance here, Y is given as Y1 plus Y2 plus Y3. That is G plus J into BC minus BL. If you elaborately write this, the admittance here will be G, admittance here will be J into BL minus J into BL, and here it will be J into BC. So if you add all the three of this, we will get this particular value. First, the case 1. In the case 1, we consider susceptance, capacitive susceptance is greater than inductive susceptance. In this case, the current leads the voltage by pi degrees. So pi is equal to tan inverse of BC minus BL by G. And here, so here, if you draw a phasor diagram, the current across the resistance, let us take it in the forward direction. Let us take it as IR, and the current across the all the so current across all the voltage across all the elements is same. Let us take that voltage as V. So that V is represented here. Now, as BC is greater than BL, obviously the capacitor the current leads. So capacitor IC is in the above direction. As BC is greater than BL, IC is greater than IL. That means if you take the IL in this direction, the arrow vector will have a lesser length. So the resultant current will be in the upward direction, which is given as IC minus IL. IC minus IL. So the resultant current in this circuit, that means I which is flowing through all of these three elements, the magnitude of that I is given as root of IR square plus IC minus IL whole square. And this is case 1. Let me minimize this case 1. Let me put it here. Yes, this is case 1. Now, when we move on to the case 2, What is case 2? In case 2, BL is greater than BC. Case 1 is BC is greater than BL. Here it is BL is greater than BC. This is not so visible. Let me expand it. So BL is greater than BC. If BL is greater than BC, the current lags the voltage. That means susceptance, if BL leads, what about the current? It lags the voltage by 5 degrees. The magnitude of that current will be root of. Here the reverse happens. As BL is greater than BC, this lower length will be more. That is IL minus IC will be in the downward direction, and VR is in the this direction. So the magnitude of the resultant current is IR square plus IL minus IC whole square. And coming to the case 3, as it is a parallel RLC circuit, it may so happen that XL will be equal to XC, okay, or BL is equal to BC, okay. Then the entire circuit will be resistive in nature because the net impedance, this Y2 equal to minus Y3, both get cancelled and only G remains. That means the net impedance will be G. And the circuit will be what? Resistive in nature. If it is resistive in nature, the net current and voltage and current will be are in phase. That means the total current is equal to current through the resistor. In this case, the power factor will be, so we'll see it later. So this is the summary. Okay, this is the summary. And when we see about, let us move on. When we see about the power factor for all the series circuits, the power factor will be cos pi is equal to R by Z. For all parallel circuits, the power factor cos pi will be equal to G by Y. This is applicable only for single frequency circuits. If it is a multiple frequency, then power factor will be real power divided by apparent power. This is applicable for all the circuits, for each and every circuit, even with multiple frequencies, like we have seen in the previous session. Okay, so this is about the summary of the AC steady state circuit analysis, what we have seen till now. Now, and in the next session, we will see about the resonance. This also comes under AC circuits only. We will see what is resonance. Okay, so we have seen somewhere about the resonance. Yeah, see here. So here we have seen that in which circuit this is what, a series RNC circuit. In the series RNC circuit, if XL is equal to XC, then that is the condition for resonance, and we will deal with this in the next class. And I thank you all for listening patiently. So we'll stop here.